Welcome back to Introduction to Computational Fluid Dynamics. In the previous class, we talked about the so-called basics of fluid dynamics, focusing on the equations of motion. We looked at these equations of motion in integral form and differential form. The differential form might be viewed as the Navier-Stokes equations. We also talked about alternative approaches which involve the Boltzmann equation. In this class, we'll talk about a series of equations that are reduced from the Navier-Stokes equations. For each of the sets of equations, we'll look at its advantages and disadvantages. We'll also look at the mathematical form of the equation. In certain cases, we'll talk about its history, and we'll show one example of its use through fluid dynamics, computational fluid dynamics, and its comparison with a corresponding experiment. These have been used and developed over the course of many years, so this will give you an idea of which particular equation to use for a particular problem. The advantages of choosing a different equation than, say, the Navier-Stokes equations themselves is that you might find a solution which is computationally cheaper, or if you're looking at a certain or particular problem, you may not be able to use the full Navier-Stokes equations because you don't have enough computer power. The major advantage of these approaches, that is the ones that are reduced from the full set of the Navier-Stokes equations, is simply that you might have enough computational power to find an appropriate solution. When I say specialized forms of governing equations, I particularly mean that the governing equations can be simplified in certain circumstances. For maybe a specific flow. It could be a high-speed flow, a creeping flow, transonic flow, maybe a flow that doesn't separate, maybe it's specifically for a boundary layer. There's lots of examples and we'll look at them here. They, in particular, are designed and reduced from the full set to capture particular physics in hand. And this, of course, sacrifices mathematical terms in the equation because they may not be dominate or they may not contribute to the particular phenomenon that you're trying to study. There's particular advantages for doing this. Of course, as I alluded to, it is easier to solve these equations simply because there's less terms. That means it's less expensive for the computer, it uses less memory, and you can find a solution faster. There's particular disadvantages, of course, is that the solutions are not as general because they don't include those other terms, and all the physics may not be particularly captured. You'll have to be very knowledgeable when choosing one of these sets of equations because you'll be sacrificing the fidelity of the solver. It's also not as general. So a CFD code that solves perhaps the potential flow equations will never be able to fully capture turbulence. Now, these specialized forms are not as applicable to all flow regimes, but they only are used typically for those that they're designed for. You shouldn't download a CFD code or try one and apply it to a particular type of flow or problem outside of its range. For example, you would probably not use a CFD code designed for hypersonics for a creeping flow. That example is obvious, but they can be much more subtle when you start looking at specific equations and solvers. It'll take time to understand this. This will give you an overview of probably the most popular and famous sets of equations which have been used through CFD through today. Do not dismiss the older solvers, especially in systems engineering settings where you need to generate thousands, if not tens of thousands, of CFD solutions to design a vehicle. That may come in handy, where today the full high-fidelity solvers like large eddy simulation or direct numerical simulation, or even a detached eddy simulation and unsteady RANs, which we'll talk about all these later in the turbulence modeling section, won't be used in a design setting for systems level design. And that's where a lot of engineers go today. We will focus on one particular type of solver in the turbulence modeling section for the simplicity of learning in the class. Before we begin, we should note that all these types of equations might be solved in two different forms. The first is dimensional and the second is non-dimensional. Remember, a dimensional number has some particular units, like a length might have a unit of meters or inches. A non-dimensional unit does not have any units at all. For example, on the right, I've shown the particular non-dimensionalization which is almost universally used in the non-dimensionalization of equations of motion in computational fluid dynamics. We write the non-dimensional form of the variables with a soup star. Here, x, y, and z, and t are space and time. U, v, and w are velocity components. P is pressure. T is temperature. Rho is density. Mu is viscosity, and E naught is the energy, total energy. Now, the soup stars mean it's the non-dimensional quantity. On the right-hand side of each of these particular equations, for example, y soup star equals y over L, is represented by the actual y-coordinate divided by some length scale L. V sub infinity might be some ambient velocity. Rho sub infinity might be some ambient density. That is, it's just the undisturbed constant density that each particular density is normalized by. You can see this is one particular and simple way to non-dimensionalize the equations. You should also know that there's many different choices of non-dimensionalizations, and some are particularly useful because in your equations of motion, very important non-dimensional numbers might appear, such as Reynolds number. We'll see some of these forms of these equations in this class. Now, for non-dimensional sets of equations, there are, of course, advantages and disadvantages relative to the dimensional form. We'll talk about the advantages and disadvantages relative to non-dimensional equations. So non-dimensionalized equations might be any set which you have non-dimensionalized, and they can all essentially be solved this way. Almost all of the original computational fluid dynamics solvers were written as non-dimensional solvers, and there's a very important reason for this, which we'll see in a second. Almost all contemporary solvers, or solvers that are being today, are almost always developed as dimensional solvers, and this has to do with computer architecture. Now, there's certain advantages for the non-dimensional approach beyond computer architecture. One is, of course, it might capture the similarity in the flows. You all ultimately, automatically, and immediately have a non-dimensionalized solution. This is a major advantage for the digital computer architecture. Early computers had very limited precision. And so by using non-dimensionalized numbers, the order of magnitude difference between various non-dimensionals group was closer. For example, you would never have to add a very, very, very large number to a very, very, very small number. When you do this type of operation, you lose precision in the result, and it might be corrupted and not have the true solution, or even a solver which is ill-behaved. Today, the precision and accuracy of our computers is much higher, and so we do not have this problem with modern CPUs because, of course, we have 64-bit CPUs and they have more precision, and we can use double precision variables, for example, in Fortran. Certain disadvantages might be we lose some kind of physical insight. That is because we're not using the real dimensional numbers. But of course, if we convert from non-dimensional numbers using the dimensionalization on the right or an equivalent one, then you can refine your non-dimensional values. You would do this anyway when calculating actual lift and drag. This means, of course, that you must redimensionalize the solution after the solver ends if it's a non-dimensional solver. So when your solver ends and you find some field variables in a file, you'll have to know what they are. Make sure you understand their units too. This is a simple mistake many people can make who are unfamiliar with their particular solver. We can always non-dimensionalize a dimensional solution too. So if you use a dimensional solver, you can non-dimensional your particular variables and find non-dimensional variables that you might compare or scale with your wind tunnel or field test. This is completely common. Now let's look at our first set of reduction equations from the Navier-Stokes equations. Remember, the Euler equations were found before the Navier-Stokes equations, and they were modified to find the Navier-Stokes equations. In this class and most contemporary classes, we find the Navier-Stokes equations and reduce them to the Euler equations by simply setting viscosity to 0. This is why on the left I said the Navier-Stokes equations are the basis, and we are essentially setting viscosity terms, the first and second coefficients, to 0 in the equations. We do not make any other assumptions. They're still compressible, and they're still three-dimensional. Now, on the right, we show the particular Euler equations. We might have continuity, which you still see in its unmodified form. Here, v bar is velocity, and we have the three momentum equations written in vector form. That's simple. You'll notice they're exactly the Navier-Stokes equations without viscosity. On the left, you'll see I've written some particular point where these equations are, valid and can be used. There's many other applications though, and we'll be pointing these out for each set. These absolutely model inviscid fluids, that is, fluids without a particular viscosity. Or they can also model and give very good solutions for flows with extremely high Reynolds number without any majority areas of turbulence, if you will. Very high speed flows. Let's mark down some of the advantages and disadvantages of the Euler equations. It will give you, if you solve this set of equations, or Navier-Stokes, of course, excellent predictions in regions where there are shock waves, where the very turbulence quantities are very, very small or negligible. The predictions will be very good far from solid walls where there's no disturbances. And it will give excellent predictions in large spatial regions away from aircraft. These are many other examples, just a few. It is an excellent model for acoustics, though not all acoustics can be solved with the Euler equations. It is a wonderful model for such problems. And of course, and most importantly, is much less computationally expensive than Navier-Stokes equations because why? We're not evaluating those viscous terms. The difference in computational expense for the Euler equations and the Navier-Stokes equations is immense because you're not worrying about resolving all the scales of turbulence like you would in the Navier-Stokes problem. Of course, making these assumptions, there's a price, and there are disadvantages. It is impossible to capture viscous effects because we have neglected the viscous effects. Therefore, the turbulence is completely lost. There is no true physical three-dimensional turbulence in the Euler equations. Also, there will be no boundary layers, and boundary layers are critical for calculating the true drag on a vehicle. You'll only be finding pressures on the boundaries, and you'll not be finding those shear stress terms that are due to the stresses from the viscous effects. However, this is okay in many situations, and we'll show one where it turns out to be a happy case. Remember, the Euler equations now are typically used in extremely high Reynolds number flows, and they're excellent at predicting any flow where the viscosity is very, very small. For example, if you take helium and supercool it, the Euler equations will exactly model its motion because the viscosity disappears as the temperature goes to zero. Let's look at one example of the Euler equations from the National Advisory Committee for Aeronautics for one of our favorite airfoils, the 0012 NACA airfoil. We will look at a speed of Mach 0.8. That's the ambient Mach number is 0.8. We denote this as m sub infinity. The angle of attack alpha will be 0. Now this airfoil will be pitching. That is meaning that the computational grid will be structured and moving in time. For example, here's the original grid in the upper left. Here's the grid going in an upper direction by 1 chord length, and here's the grid in a downward direction by 1 chord length. They've designed the grid to try and capture the region of the airfoil wake in advance of the solution. So in some sense, they've known something about the solution in advance. This isn't always the case today, but here's a good test case. You can see the grid is structured. Remember, it has an ordered mesh, and it was a finite difference approach. Now, here is the airfoil coordinates, and they've non-dimensionalized the NACA 0012 airfoil by its chord C. This is not the speed of sound. X is the streamlined position of the airfoil coordinate. This is the leading edge of the airfoil, and this is the trailing edge. On the y-axis, they have the non-dimensionalized pressure written as the pressure coefficient, negative Cp. Now, they've written negative Cp because typically you would put negative values of Cp on the positive part of the y-axis. And you would always see graphs that look like this. In aerospace engineering, it is traditionally the case where you would write the negative values of Cp towards the top of the axis and the positive values of Cp down the bottom. Now, the experiment from the NACA is shown as the circles on the CP graph. The line is the the CFD result from the CFL 3D code, which is also developed at NASA. The CFD code is drawn as the solid line. You can see that there's very good agreement, except in the region where the shock wave occurs. And see, this is the pressure increase of the shock from the flow going from left to right. So this result is correct. And the Euler equations have made some good predictions. So this is a case where the flow hasn't separated. It's a relatively high-speed subsonic flow, and it's made a good prediction, solving the Euler equations, which are much cheaper than, of course, the full Navier-Stokes equations. The Euler equations are, of course, named after Leonhard Euler. Here's his picture on the right. It's a painting of him in St. Petersburg. You might be interested in what he's wearing. Those are actually Persian robes. At the time while he was working there under the Tsar, it was very famous and popular to wear Persian robes as an import for your portrait. So this is not really in the Russian tradition. Euler was born in 1707, and he passed away in 1783. He was Swiss, but worked in the court of the Tsar in Russia. He was, of course, a mathematician, a physicist, astronomer, logistician, and engineer. He did many things, and he was a very, very hard worker. There's many wonderful stories about Euler, which I encourage you to read in History Online. You've probably heard of his name and will continue so in many different fields. He's likely the most prolific mathematician of all time, and they're still collecting his works and publishing them in volumes which would already fill more than 80. Most of his adult life was in St. Petersburg and then Berlin, which was the capital of Prussia. He married Catherine Gesell, and he had many children, but only a few lived. Only 5 of his children lived, and the other 8, unfortunately passed away. He was a very devout Christian, and in his life, unfortunately, he went blind, and he underwent cataract surgery twice. At the loss of his second eye, he said, "Now have less distractions." And actually, he was just as prolific and productive as a mathematician after he went blind. Let's look at our next set of equations, the full potential flow equations. This is another reduction. This is using the major assumption that outside of a thin attached viscous boundary layer, the flow can be assumed to be irrotational. That is, this set of equations are assuming the irrotational effect. It is very typical that in your aerodynamics or fluid dynamics classes, you have examined the potential flow equations. If you haven't, please go back and look. With these sets of equations, you have found traditional theoretical aerodynamic solutions for simple bodies, like the rotating cylinder near the ground to explain the ground effect. These are very interesting things, and we can also solve the full form of compressible full potential equations in this class. We will assume that the onset of the flow, that is where the flow enters our domain, is uniform and there's no shocks for external calculations. And of course, there's the major assumption that the flow is irrotational. Remember, the Euler equations and Navier-Stokes equations can easily capture rotational flow. So this is a huge assumption, but it turns out external to this region, near the viscous boundary layer, for example, in attached high-speed calculations, this is a wonderful assumption, and you'll get very good results, as we'll see in a second. Here we've written some equations down for the assumptions. One, of course, is that the curl velocity will be 0, meaning the flow is irrotational. That's nabla cross v, velocity is 0. Next, of course, is that we are saying and assuming that the velocity can be expressed as a scalar. That is, the velocity equals nabla phi. Next, we can define from the above equation the velocity components themselves. U will be partial phi partial x, v will be partial phi partial y, and w will be partial phi partial z. Now let's look at the form of the potential flow equations. In this particular first equation, we have the full potential flow equation in compressible form. This is where we inserted phi for the velocity components in the continuity equation. Then, this enforces mass conservation, mind you. Then we can recover density through the Bernoulli equation, which hopefully you've examined previously. This was, of course, named after Jacob Bernoulli of the Bernoulli brothers. There's actually 3 Bernoullis, the father and the 2 sons, and they were all very competitive with each other. Jacob Bernoulli was one of the most prolific, and that's who we're referring to for the Bernoulli equation. It's going to write that density is going to be a function of Mach number and the potential terms, phi. The full potential term, There's also many alternative ways to write this equation, as you'll see, and you'll have to figure out which CFD solver you're actually which equation the CFD solver is actually using. So here's one particular form written as a single equation. This might be phi sub tt, which is the second derivative of phi with respect to time. So you see it's a time-dependent equation 2, which is compressible. Remember, like in your classes, you've probably solved the 2-dimensional incompressible steady form of this equation. You can actually find that equation from these equations by making those simplifying assumptions. In this particular equation, they've actually written the speed of sound, and they called it traditionally a. So a is a local speed of the sound, and a sub infinity is the ambient speed of sound. This might only be a function of temperature itself. A is a function of the spatial position and the flow velocities. And of course, it'll be only a function of, say, phi sub t, a, and Mach number, which is a function of u, the magnitude of velocity, over the local speed of sound, a. So, this is m infinity. So that'd be u sub infinity over a sub infinity, the ambient speed of sound. Let's look at some advantages and disadvantages of this approach. Of course, this is extremely inexpensive today compared to the full Navier-Stokes equations. And so it also contains most of the advantages of the Euler equations. That is, away from the bodies, the flow will be irrotational and compressible. Unfortunately, there are some disadvantages. The flow may be, of course, viscous, and then we couldn't use these equations, and of course we made the irrotational assumption. And there is, of course, once again, no chance whatsoever to capture turbulence, but this is truly the case for the Euler equations too, so we've already made that assumption earlier. Typically, this equation is used and integrated for high-speed compressible vehicles for system engineering and design problems. These types of equations might be integrated into a single processor solver, which might run thousands, if not millions of times for a single aircraft type of design, or any other type of vehicle where these types of equations are appropriate. Once they down-select to a design, they might run higher fidelity solvers with Navier-Stokes or Euler with turbulence models to find the final design where they might go into a wind tunnel for testing. Let's look at one particular example of a flow past a nominal commercial aircraft. This is once again adapted from NASA. On the left, you see a structured computational domain. In the middle, we have a graph, and it's typical like the previous one, which we examined for C sub p. At the origin, we have x over c0 and x over c1. These are at different locations from the leading edge of the wing to the trailing edge of the wing at 3 different span-wise positions. For example, out here where my cursor is, this is the tip. In the root is the root of the wing, which corresponds to where it meets the fuselage. Now you see at these 3 positions, from the root to the tip of the wing, going to the right on the wing, you'll see values of Cp. Once again, experiments are represented as symbols, and the pressure and suction side of the airfoil, the bottoms are pressure and the suction sides are the top of each particular graph. You'll see lines of the CFD solution from the full potential flow equations. Now you'll see, once again, they have Cp and they have negative values of Cp plotted on the positive axis. You can see this tradition once again. Remember to plot your results that way. Note they also non-dimensionalize the span-wise position of the plot by the value of eta. For example, near the root, the first value is eta 0.28. Let's now make another reduction. Say we use the full potential equations and say that there's only small perturbances in the flow about some ambient value. We call these the small disturbance equations, and they can be valid over any type of Mach number as long as the disturbances or the flow variables are only a tiny bit away from the so-called base flow. Here the base flow might just be some ambient velocity or Mach number. We'll assume that the aerodynamic body has only a small effect on the surrounding fluid. Now we'll write our potentials, partial x, and partial partial y, as these terms on the right side of the equations. For example, phi will be the ambient velocity, it might be 500 meters per second, times some position x, plus phi. So that means the solution variable we're seeking now is little phi and not necessarily big phi. We'll seek little phi and substitute back into big phi to, capital phi to find the actual solution. Also, for example, you might say phi sub y equals nothing but v, the cross-stream velocity component, and phi sub y, that's partial phi partial y. So phi must be extremely small because it's a perturbation technique. Perturbation techniques are very popular in partial differential equations to solve particular equations, especially in fields such as vibrations and acoustics, where there's linearization of the problem. So this is essentially linearization. Once we do that, we can of course simplify our equations by substituting this form into the full potential equations and crossing out terms which are very, very small relative to terms which are, of course, linear. That is, we're canceling out the nonlinear terms. Remember, 2 very small terms like phi sub x and phi sub y, for example, would be even smaller and negligible compared to other terms in the equations. This is the advantage, of course, of perturbation approaches. The assumption can be written this way, that u prime and v prime are much, much smaller than the ambient velocity. For example, u prime might be 1 to 5 meters per second, as any type of case, and u infinity or v infinity, that's the magnitude of the ambient velocity, might be 300 meters per second. This is the perturbation itself. We are assuming the disturbances are small, and you might find this equation on the bottom of the page where we've written in terms of the ambient Mach number, gamma, which is the ratio of specific heats, and phi sub x, phi sub xx, phi sub y, phi sub xy, and phi sub yy. and that will all be equal to 0. So you can see in this case, if we solve this equation, we have a single differential equation for phi. M sub infinity and V sub infinity would be constants, or the boundary conditions of the problem. That's the speed of the flow which it enters the domain. Let's look at one particular example from NASA. On the left, we have a particular airfoil. The flow moves from left to right. On the right, we have the results from the small disturbance equation for this so-called unsteady lift and sinusoidal gust problem. So the inlet boundary condition, or the flow coming into the airfoil from left to right, actually has a sinusoidal nature. And they've solved the SDE equations and plotted their results relative to the experimental data. In this case, the solution is the line, and we have a y-axis of CL, the coefficient of lift. The x-axis is essentially time. Now you'll see that the CFD solution, which is the line, corresponds relatively well to one of the particular experiments with non-reflecting. Let's move on and make another assumption. You can always make more assumptions if it remains valid for your particular problem. We'll say now that the small disturbance equations are located near regions of transonic flow. That is, the Mach number is near 1. It could be 0.9 or 1.1, somewhere in that range. The range of transonic flow depends on the particular vehicle and the atmospheric properties. So we'll say the flow for now is transonic, and it will contain perhaps multiple shock waves which are close to being normal shock wave. That means that the face of the shock wave is normal relative to the flow direction. So in transonic flows, it turns out that the partial derivatives in the x direction will be much bigger than partial derivatives in the y direction. Perhaps you can stop and think about a particular flow. Maybe it's a very thin airfoil in the transonic regime where a normal shock appears. You can imagine if you take particular derivatives of any variable like densities or velocities or pressures in the x direction across the shock, they'll be much larger than the y direction. This is why in the transonic regime, this is a good prediction, and we can simplify our small disturbance equation even further if we limit it to Mach numbers in the transonic range. Our small disturbance equation now becomes this particular form. And if we simplify it a little bit more and say it's steady, we get the form on the bottom of the page, where of course there's no temporal variation. That is, there's no phi sub tt terms, partial 2 phi, partial t squared. Let's look at some advantages and disadvantages of the small disturbance equation versus transonic small disturbance equations. There's particular advantages, of course, that there'll be excellent predictions for slender bodies that do not highly alter the flow field. This is wonderful. So if you have a very slender, high-speed body, you can simply solve the SDE equations very, very cheaply relative to modern solvers. Unfortunately, the advantages are if you have any kind of body that's at a high angle of attack, it's not very slender, or there's places where there's large flow separations or any large disturbance relative to the baseline incoming flow, then you can't use these equations. The transonic equations in particular can be used in Mach ranges of perhaps maybe 0.6 to 1.2 for a typical body. The slender aerodynamic bodies in the flow fields must not have separation, and they must have a low angle of attack. This is very important to remember. Let's turn our attention to a little bit of a different set, and this is the so-called Prandtl-Glauert equations. We've talked about these equations before in the part of the class where we're looking at flow visualizations and comparing them to CFD solutions. This was near the beginning of the class. Now we'll look at their actual equations. These are very similar to the full potential equations. In this form, they've written their equation as 1 minus m infinity squared of phi xx plus phi yy plus phi cz minus 2m infinity squared over u infinity times phi xt, this is a mixed partial derivative, minus m infinity squared v infinity squared phi tt equal to 0. This is the Prandtl-Glauert equation. And for certain values of this particular equation, you can find pressures. And these pressures might drop below the vapor pressure, and you can find the lines where the clouds form around aircraft when you see them moving around the atmosphere. That is a natural visualization. It is, as you'll note, a linear equation and is valid in subsonic flows and can be transformed to the Laplace equation through a transform. In supersonic flows, that is where m infinity is greater than 1 and the flow velocities are all going to be greater than 1, U over C, that is, excuse me, all the Mach numbers will be greater than 1. It can then be transformed into the wave equation. In this class, we looked at the wave equation before, and it just so happens that for some particular boundary conditions and flow velocities, there's analytical solutions for the Prandtl-Glauert equation because it can be transformed to the wave equation. There's also analytical solutions for the Laplace equation, and we inverse transform those solutions with boundary conditions to the Prandtl-Glauert equation. We can also find analytical solutions for these particular flows at subsonic and supersonic speeds. That's amazing, and it's very thankful we have these particular analytical solutions. However, if we have realistic boundary conditions, then there won't be analytical solutions for those simplified equations, but they are certainly much cheaper to solve than almost any other set of equations numerically that we've seen in this class, now and in the future. Now, if we find a numerical solution for the Prandtl-Glauert equation through its transformed equations of the wave equation or Laplace equation, then we can easily recover the pressure coefficient C sub p, which will go as negative 2 phi sub x, that's partial phi partial x, minus 2 over the ambient incoming velocity times partial phi partial t. Now, there's also a steady form of this equation, which I've written at the bottom of the page. This is, of course, where we simply get rid of the phi sub tt and phi sub xt terms and let the equation remain equal to 0. You can see this is an even simpler form of the equation, which is very easy to solve even with the most simplified CFD programs. So this is used once in a while today, but it's really been phased out. However, we talk about this equation because it contains a lot of physics and simplifications that captures the predominant amount of a lot of different types of flows around aircraft. So it's critical to understand this equation over time and understand the physics behind it and its implications. There's certain advantages, of course, is that it is extremely cheap computationally. It can be solved analytically in some particular cases for certain boundary conditions. These are very few analytical solutions, but there's a wide range of closed form solutions for the wave equation and Laplace equation. It is a linear equation. The Navier-Stokes and Euler equations are nonlinear, and so we can use linear solvers for that. For example, the linear algebra solvers from linear algebra. There's a simple pressure recovery from the solution, as I shown in the previous slide. Of course, there's some disadvantages. The flow must be entirely supersonic or subsonic. That is, everywhere in the flow field, the Mach number must be either greater than 1, or less than 1. It has very specific cases today. Typically now, it's used for bodies which are moving through atmospheres at very high subsonic speeds or low supersonic speeds. And the linear form of the equations allows them to be solved with linear algebra solvers, which greatly simplifies the approach. Let's look at one particular example of the Prandtl-Glauert equation. This is one particular analytical study, meaning it wasn't done with CFD. It was done on pen and paper for the so-called pressure coefficient versus inflow Mach number for various bodies, such as ellipsoids. So these are various ellipsoids with different eccentricities. Now on the x-axis, we have Mach number from 0, 0.2, 4, 0.6, 0.8, 1, Mach 1, this is transonic, and 1.2. Notice they did not look at solutions at supersonic speeds. Now they've plotted on this graph a sphere for reference, and they've put in different thickness over chords from each particular ellipse. For example, here, this line here represents a graph of the thickness over chord of ellipse. On the y-axis, they've put essentially a non-dimensional pressure coefficient, and it varies from 1 at Mach 0 all the way up to 20 for some particular cases. Now, for particularly small values of TOC, thickness over chord of the ellipse, that is the thickness going to 0, they find theoretically that there is an analytical asymptotic solution, and that is that the normalized pressure coefficient is going to go as 1 over the square root of 1 minus the Mach number squared. That's a fascinating equation. Now they've plotted the other analytical results up to about Mach 0.9. You'll notice that in all these cases, they're all very close near 0, which makes sense because they all should have a pressure coefficient of essentially 0 at Mach 0. And as it rises, they all diverge, and they're all rising very quickly. One might say, and they did traditionally, and I quote, that the drag rises like a barrier as the Mach number approaches the speed of sound. Notice the key word barrier. That is where the term sound barrier came from. That it wasn't viewed that we can't go through the speed of sound, the transonic condition, but it was seen as a barrier. So a lot of people still call the sound barrier a barrier today, even though, of course, everybody originally believed, in the scientific communities at least, that we can, of course, go through it. From an engineering point of view, it was a major challenge. And of course, the Bell X-1 was the first manned aircraft that went through the sound barrier and broke the so-called sound barrier. I talk more about this history in my compressible flow class. Anyway, as T over C goes to 0, we recover this analytical solution. So you can see this Prandtl-Glauert equation is very famous because, of course, it helped coin the phrase that the sound approaches a barrier as the Mach number goes to the speed of sound. Let's look at a little bit of history of Ludwig Prandtl. He was born in 1875 and passed away in 1953. Here's two particular pictures of him. He was a German, and he followed the German educational system and traditions. Here he is with a little water tunnel, which was driven by a water wheel nonetheless, and there is his more formal picture. He is extremely famous today in the field of fluid dynamics and CFD. In fact, earlier we showed the Prandtl number, a non-dimensionalization that comes out of the non-dimensionalization of the Navier-Stokes equations. He was known for aerodynamics, transonics, boundary layers, thin aerofoils, lifting theories, the so-called Prandtl-Glauert correction, which we'll talk about later, and many more discoveries. You'll hear about him more and more. He wrote a paper called Fluid Flow and Very Little Friction, and this is where the idea of the boundary layer was first developed. It was a conference paper which he presented as a single author paper. This was in a landmark and amazing paper showing that the disturbances in the fluid, the viscous effects, are located in a very thin region which are attached to the wall in a flow, and the rest of the flow is relatively undisturbed. This paper should have won a Nobel Prize, but unfortunately there's a little bit of politics behind it because he was in Germany and worked for the Germans in World War II. One of his students was Theodor Meyer, and Theodor Meyer and Prandtl developed the entire theory of supersonics in terms of shock waves and the so-called Prandtl-Meyer expansion waves. We talk about these at length in compressible flow if you've taken it. He was also the director of the Kaiser Wilhelm Society. He had a number of doctoral students. If you stay in this field, in industry, research, academics, or government, you will see these names come up over and over. We've already talked about some of these names in this class. Some of these are accurate. Blasius, after the laminar Blasius solution. Bussmann. Munk, who was the lead and leading aerodynamicist and theoretician in the United States, who worked at NASA Langley. Another one is Schlichting, who studied turbulent boundary layers, opposed to a student who studied laminar boundary layers. Tolman, who looked at Tolman-Schlichting waves with his colleague. Von Karman was his student who came over to the United States and started the Jet Propulsion Lab at Caltech and NASA JPL. I'm sure everybody's heard of NASA JPL. It's a major center. And that was von Karman who found it. And it's interesting that his own student von Karman and Prandtl, Ludwig Prandtl, were rivals throughout their later careers. And many others. He had 85 in total, and I'm sure you'll come across them. Anyway, after the World War II, his lab was in basically decimated, and he passed away in 1953. Let's next look at the thin wall Navier-Stokes equations. These will maintain some sort of boundary layer calculation but allow separated flow. That is, we retain a viscous effect. So we return to the Navier-Stokes equations and we say, except for a very thin layer, which is the boundary layer, we will retain these viscous effects. We also retain terms that allow for the flow to be separated and the flow separation to be accounted for. This pressure will allow the pressure to be varied across the boundary layer. That's unlike later equations we'll see. It can handle high Reynolds number flow and viscous effects confined to the very, very thin region. And all the viscous terms in the streamwise direction are assumed to be essentially small. That's one of the major assumptions. Now we'll compare these so-called viscous effects to maybe a particular body in a second. And the flow will always be maintained in the streamwise direction, even if it separates. So we would not be able to look at perhaps some big recirculating region. Here's a particular diagram which shows the so-called thin layer Navier-Stokes equations. This is the boundary layer, and these are flow velocity vectors in the x direction plotted as a function of y. The viscous effects are reduced to the form in the lower right. Here are the equations themselves for the particular momentum. You can see that the right-hand side is greatly simplified. They're still compressible, three-dimensional, and unsteady. Here's the material total derivative of UV and W. This is the pressure terms, and of course now the viscous terms only involve one particular component. Here, for example, we have partial y of mu of partial u partial y. This is much simpler than evaluating the whole viscous stress tensor. So these are also very much like the Euler equations, but one particular term of viscosity on the right-hand side. So if we make these assumptions, we cannot hope to ever predict fully three-dimensional compressible turbulence. We are making assumptions about the flow and the turbulence itself, and might actually solve these equations in somewhat of a more steady state or a state with a turbulence model. Typically, these are solved with structured grids that conform to bodies. Another set of important equations are the so-called parabolized Navier-Stokes equations. These are very, very popular today for supersonic flows and hypersonic flows, opposed to just full CFD solvers. They are essentially assuming that there's no streamlined flow separation and the flow everywhere outside the boundary layer is supersonic or hypersonic. They almost always make a steady flow assumption. Now, there'll be, instead of a technique to solve the equations that marches them in time, they will find steady solutions which march in space. A steady marching solution is one where we assume the condition upstream, might be Mach 2 uniform flow, and march the solution downstream towards the body and over the body and march it downstream after it. So instead of advancing in time, we advance in space. Now, they're not truly parabolic in the mathematical sense, but this is the way they're evaluated nonetheless with some numerical tricks. We'll look at one example down here in the bottom of these equations where we might have a boundary layer flow and we're simply marching it downstream. You'll see inside the turbulent boundary layer where there's a sonic line, the equations are elliptic and there'll be upstream traveling waves. In the supersonic region of the flow outside the boundary layer, we have, of course, hyperbolic equations, and we would march the solution downstream. In this particular case, we would assume something about the boundary layer. That's not always the case and not something we always do in practice. Here's the actual full form of the parabolized Navier-Stokes equations. You'll see that we've written in vector form. This is another form in CFD which you might see a lot, writing the Navier-Stokes equations, or in this case the parabolized Navier-Stokes equations in vector form. Let's take a few minutes to understand it. The first, second, third, and fourth are the equations of motion. The full equations of motion, in fact, for continuity, momentum, and energy. For example, the vector E is written here. So each of these four equations, their vectors are written near the bottom. So for example, the first component of E is rho U. The first component of F is rho V, and the first component of G is rho W. And then the first components of EV, FV, and GV, which stand for viscous, the little v means viscous, is 0. So if you go back to the first equation, we can look at it and say, well, the first component's rho U, and it has partial psi. So they're written in the metric notation, that is for a structured grid. You can also transform this for a finite element or finite volume approach if you do the mathematics. So what does this first equation mean? It's partial rho U, partial psi, plus partial rho V, partial eta, plus partial rho W, partial zeta equals 0. You'll see that the first component of these vectors inserted in these equations is going to give you the continuity equation. The second component inserted in for this set of equations would give you the momentum equation, the x direction. Third component, y direction momentum. Third component, z direction momentum. And last component will be an energy term. And of course, down here you see all the viscous terms which fall into the right-hand sides of the equations. So we've compactly written the vector form of the equations. You'll see this a lot in research papers. I would recommend trying to insert a few of these vector forms and try and recover a different equation beyond continuity. That way you'll fully understand these forms for the future. There's certain advantages to parabolized Navier-Stokes equations. Of course, this is a spatial marching technique. It is very, very fast compared to other techniques because you're just marching the solution downstream. For every step in the streamwise direction that you march with the solution, you have the solution and you're simply done. There are many excellent predictions for many applications using this set of equations. There's certain disadvantages. They will not capture regions of transonic flow or regions where, of course, there's large separations where recirculations occur. In a recirculation, your flow might be returning upstream, even though you're in a supersonic, streamwise flow from the inlet condition. These are typically used in hypersonics and high-speed aerodynamic calculations. Let's look at one example of the parabolized Navier-Stokes equations example. Here we look at flow past a cone. The incoming Mach number is 10. That is meaning that the vehicle is moving at 10 times the speed of sound. The angle of the vehicle is 5 degrees. That means it's pitched up by 5 degrees relative to the incoming flow direction. This is drawn here. We have m infinity, which is 10. There's an x and y axis, and then the cone surface is drawn by this grayish lines with dashes. Now, let's look at particular measurements and predictions. On the x-axis here, we have pressure over the ambient pressure, and on the y-axis, we have y over L. Here, L is some characteristic length of the body. Y is the distance from the x-axis to any position on the body. For example, y over L of 0 is the position at the leading edge. Y over L of 0.3 is near the trailing edge of this particular cone, which is going through the atmosphere. Now, experiments are presented by Hoffman and his colleagues as symbols. The present predictions using the parabolized Navier-Stokes equations are drawn as lines. You can see from the leading edge to the trailing edge that there are very accurate predictions from the code relative to the measurements for the steady pressure. You can see there's a very, very large change in pressure at about y over L of 0.15. What is this? This is a transitional point within the flow. Let's next look at a very, very famous set of equations, which we will be looking at and referring to in the turbulence modeling section. Let us return to the Navier-Stokes equations themselves and say that the flow is simply a boundary layer. Like Prandtl, we'll say that the boundary layer is a very thin layer of fluid with turbulence characteristics that is attached to the wall. These equations are put in a non-dimensional form. We'll say that the boundary layer thickness, that is the distance from the wall to the edge of the turbulence of the entrained fluid of the boundary layer, is much less than the characteristic length of the flow, which might be the distance from the leading edge of the boundary plate to any position on the boundary. We'll look at the two-dimensional boundary layer equations. We'll set that there's some small parameter defined as the boundary layer thickness divided by the characteristic length, and therefore epsilon is very, very, very small because delta, of course, is very, very small. This might be on the order of a few millimeters or centimeters, and the length of the vehicle might be something like 100 meters. Terms like the velocity component or x are going to be on orders of 1, and terms like v, the velocity component in the y direction, and y itself are on the orders of epsilon. If we do an order of magnitude analysis on the Navier-Stokes equations and set them as to be steady and incompressible, we'll find this particular continuity equation, this particular momentum equation, and this particular y momentum equation. In this case, the Reynolds number with this non-dimensionalization automatically falls out because of the choice of the non-dimensionalization. So that was a very careful choice done through trial and error to see the Reynolds number appear as one over Reynolds number. What is very physical is you don't see this Reynolds number appear in the y momentum equation. All you have is partial p partial y is 0. This means that the static pressure is not changing as you transverse the boundary layer in the cross-stream direction. The x momentum equation is most interesting and physical. You'll see that the Reynolds number is only in the viscous term. So this means as the Reynolds number becomes larger and larger, the viscous effects become smaller and smaller. This is very important and why you might just approximate for very high Reynolds number flow the floors of Euler equations. But of course, then you never capture the boundary layer. You'll see you still have a pressure gradient in the x direction. Many boundary layers are studied with partial p partial x is 0. And then of course you'll just find the left-hand side equal to the right-hand side viscous term. This is the so-called zero pressure gradient boundary layer case. And that's simply setting partial p partial x to 0. The continuity equation remains as incompressible and steady. There's certain advantages and disadvantages for the boundary layer equations. They are excellent at predicting terms like skin friction, boundary layer displacement, boundary layer momentum thickness, locations of separation, heat transfer, and of course surface temperatures in boundary layers. for these particular cases. Note that there's also more general forms of the boundary layer equations that are incompressible. They're extremely fast at computations and can even be put in marching approaches. The first turbulence models for CFD were put in forms for boundary layer equations, typically. Unfortunately, there's some disadvantages. They're restricted to boundary layer flows, of course, and there's no true separation possible in the predictions. So if there's separation occurring in the experiment, they will not be predicted by the CFD. They're typically, of course, used for boundary layer calculations at Mach numbers and Reynolds numbers over a wide range, and they're great for fundamental studies of boundary layers and, of course, turbulence model development. Let's look at one particular example, and we'll talk about boundary layer plots like this later. For now, know that the x-axis is the non-dimensional distance from the wall, y. The y-axis is essentially the velocity normalized by u sub ta, which is a non-dimensional velocity derived from the shear stress at the wall. Anyway, these are log-log plots. Here, measurements are shown as symbols, and the prediction is shown as the line in this case. You'll see that there's generally good agreement in the case. We'll talk about more of this later, because it's going to take a lot of class time. Let's make a few closing comments. Remember, there are many specialized equations. I've chosen ones which I think are most important for you to know and to be aware of. But just know there might be some modifications of the equations that you can make to simplify your simulation and save immense computational cost. If you're just a user of CFD, you'll probably just pick up different codes for different tasks. Remember, CFD code for a user is a tool, and the right tool should be used for the right job. They can be used to your advantage if you're wise. On the other hand, they can get you in a lot of trouble, and you may completely miss certain physical phenomena. For example, if you violate any of the assumptions of the equations and something physical happens in the actual flow that you don't predict, then you'll have completely missed it, and your result will not be correct. We've discussed a certain set of these equations with regard to turbulence modeling, and these will become clearer and more important to you for you to understand later. Next time, we're going to introduce boundary conditions. We've talked about the equations of motion at length, their physical use and solutions, but you can't solve these equations without boundary conditions. We'll review boundary conditions. What are boundary conditions? We'll talk about the basics of boundary conditions, and we'll start giving you examples of boundary conditions for simplified ordinary differential equations and partial differential equations and their implication. In a later class, we'll talk about many different specific boundary conditions for fluid dynamics, especially for practical codes today. We'll also talk about their best practices. Thank you very much for your time. I'm your professor, Steve Miller.